Today we will discuss entropy, production and entropy flow in open systems. We consider a system consisting of two phases. Suppose phase 1 and phase 2. And what is the special about these phases is that each phase is basically an open system, so that if it is open it can simply exchange energy as well as matter, exchange both matter and energy with other phase. Now the system made up of these two phases, we will consider that the entire system, that means the phase 1 and phase 2, is suppose a closed one, and it can exchange simply only energy and not matter. So we will consider these 3 points first. Now we know for an open system thermodynamic equation, that means du will be equal to TdS minus PdV plus summation. Now matter is also exchanged as it is an open system, so we will write it as gamma mu gamma E n gamma. We will name this as equation 1, or we can simplify this equation simply by writing in this form. We will first write TdS will be simply equal to du plus PdV minus summation gamma mu gamma D and gamma. So this will be equation 2. Also the number of components in each phase. Suppose it is equal to C, and this gamma has values from 1, 2, so 3, so on up to C. Also, we know from thermodynamics that the change in internal energy is basically equal to dq minus P. That's equation 3. And from the previous knowledge, we know this change in number of moles of the gamma component can also be written as reaction rate of gamma component and extent of reaction d zeta. This is equation 4. Therefore, equation, this is equation second here, second becomes, if we use 3 and 4 here, we will simply write change in entropy will be equal to dq upon P minus 1 upon T summation gamma mu gamma and dz. This is equation. Also, we know the affinity A is related by this expression minus summation gamma mu gamma and mu gamma. So this is equation 6. Therefore, equation 5 can be written as, we will simply write it in this form, introducing the value of this A, that means affinity, in place of this much. So we will write simply equal to dq upon T plus A upon T and simply d zeta. This is equation 7. Since we are actually dealing with an open system, with an open system, we must basically replace the heat transfer, that means the dq, heat transfer term, which is here dq, by simply d phi. If we are taking an open system, we will simply replace this dq, with this d phi term. But the condition is if it is an open system. Okay. This d phi, it basically represents the energy flow due to heat transfer. transfer and also exchange of matter. Now not only heat transfer but exchange of matter also, that is why we have replaced this dq with the d5. There is also probability of the occurrence of a chemical reaction. We have considered heat transfer is also taking place, exchange of matter, and we will also consider suppose a chemical reaction is also taking place. Chemical reaction in each phase. That means we must also then take into account the entropy exchange with surroundings. That is, we can simply write a simple equation here, which is TES, that means entropy exchange with surroundings, it will be represented as d phi upon T minus summation gamma mu gamma upon T dE and gamma. We will name it as equation 8. So this equation 7 can also be written as we will write ds will then be equal to d phi upon T minus summation gamma mu gamma upon T TE and gamma plus A upon T d zeta. So this is equation 9. So for the phases first and second, this equation 9 is written as, we will now take these phases individually, so we will can transform this equation as, that means ds can be written as d1 first phase phi upon T1, that means the T first phase temperature plus the second phi temperature of the second phase minus summation gamma. Also we will break this mu gamma upon T into 2, that means mu gamma suppose first phase upon temperature first phase minus mu gamma second phase upon temperature of the second phase, and it is dE and gamma, suppose this is first phase, plus This term can also be split into two. For these two phases, we will write it as A first, B zeta, suppose for first phase, upon E1, plus A affinity for the second phase and B zeta for the second phase. Similarly, temperature for the second phase. This is equation 10. Here simply this A1 and A second are the affinities of suppose reactions occurring in phases 1 and 2. Second respectively. And the dE and gamma, suppose for the first, it basically represents the number of moles of component gamma entering phase 1 from phase 2nd. So similarly, for the energy flow, we can simply write T1 pi upon T1 can be split into two parts, external and internal. So we will write it as Te1 pi upon T1 plus Di second pi upon T2. So sorry, this is first. Sorry, this is actually for only the, we are splitting the first phase only, so it will be Di first. So this is equation again. And similarly for second, we will write it as the second pi upon the second will be equal to dE second phi T second, temperature second, plus Di second pi upon T second. This is equation 12. So if anyone has any doubt regarding these equations, we have already derived and discussed these relations in the previous video lectures. So please go through those and you will get the terms here. So if I have got these, we will substitute simply. Substituting for D1 pi upon T1 and D second pi upon T second in equation 10. So we will simply get this relation then, which is ds will be equal to dE1 q upon T1 plus dE second Q upon T second plus Ti phi. We will make these two terms together, so it will transform into this one upon T1 minus 1 upon T second. We will simply take the common di phi first, or first and second, and minus summation gamma mu gamma first upon T1 minus mu gamma second upon T second. And we will also make it into a simple form here by simply taking the summation and dE and y first as common and writing the other terms. So plus A1 d zeta 1 upon T1 plus a second d zeta second upon T second. So this is equation 13. Here you will see these first two terms, that means these two, they simply represent entropy flow. Represent entropy flow, which is represented by dEs, and this is simply arising from Q is involved, so it will be simply heat exchange. Heat exchange between the closed system and the external surroundings. Now the terms third, fourth, fifth and sixth, here these terms, that means this is term third, term fourth, fifth and sixth, that means these all together, they simply represent entropy production. Entropy production, so we will write this as DIS. Now here you will see this is the third term, this is fourth one, this is fifth, and this is suppose sixth. The third term here represents entropy change, but due to energy exchange. Energy exchange between phase 1 and phase second. Also this fourth term point you can write fourth term represents entropy change due to the exchange of matter, simply between these two phases. And the last two terms, that means the fifth and sixth terms, they simply represent the entropy change resulting from chemical reactions. But these are simply taking place in each phase. So now we can write the rate of entropy production is then given by this is simply for the open system. So we will write entropy production rate is simply represented by sigma, which will be equal to BIS with respect to time. It will be equal to T15 upon Tt, and in parentheses we can write 1 upon T1 minus 1 upon T second minus summation gamma mu gamma first upon T1 minus mu gamma second upon T second, and dE and gamma 1 upon dt plus A1 upon T1, and it will be mu1, that means the reaction rate, plus one more term will be here, A second upon T second and mu second, that means the reaction rate, it will be greater or equal to 0. This is equation 14. Here you have to remember these are simply, suppose these will be considered as coefficients in parentheses, and these will be simply the rate terms. So simply here it will be also rate term, this will be also rate, this is also reaction rate, that means the rate term. So in equation 14, the coefficients of each rate, that means the flow term here enclosed in closed, suppose in these brackets, or you can say parenthesis. Parenthesis is simply the force term. Now we can thus express the rate of entropy production as a simply the sum of the products of generalized forces, or you can say affinities. Simply denoted by x, suppose subscript j, small j, and the corresponding fluxes, or you can say flows, denoted by suppose j, small j. So thus we will have a simple form of this equation. That means we can simply write this rate of entropy production for an open system will be equal to dis upon dt will be equal to, we have here considered it as sum of the products. That means we will simply summation of these j, gj and xj. Here the product of generalized force, which is represented by x subscript j, and corresponding fluxes by jj. So simply we will write this equation, it will be greater than 0. So this is the net reaction, or you can say net equation for a system or an open system. Okay. Thank you.